All right, so another example of the law of conservation of energy that works obviously exactly the same as a roller coaster is a pendulum. Okay? So if I want to get this pendulum to start moving, what do I have to do to it? Okay, where?
Any direction.
Okay.
Move
it to the side, right. Okay, because if I move it to the side, because it's attached by a spring, it also moves up, which gives it potential energy. And now, of course, the whole system has mechanical energy. If I let it go, that potential energy turns into kinetic, and then it goes up on the other side, and turns back into potential, and it just keeps going, just like a roller coaster. The graphs would go past each other. Okay, just like for the roller coaster, it's just converting kinetic into potential as it goes back and forth. Okay, so that's all we're going to look at for a pendulum in this unit, but pendulums are really important in Unit 4. Okay, where we look at what the restoring forces and all of that kind of stuff are. But from an energy perspective, they're pretty simple. Kinetic, potential, back and forth. Okay, pretty easy. All right. So in this question here, they give us a bunch of information. They tell us the pendulum's 2 meters long. They tell us at the highest point, it's 25 centimeters above the floor. At the lowest point, it's 5 centimeters above the floor. And they tell me the mass of the pendulum bob. Okay, by the way, the mass on the end of a pendulum is called the bob. Don't ask me why. Okay, I have no idea. Okay, but that's what it's called. Okay. So what's the mechanical energy of the pendulum relative to the floor when the bob is at its highest point? Okay, at its highest point, it only has what kind of energy? It only has potential. All right, so we can calculate its mechanical energy. Okay, that's EP plus EK, but we just established that that's 0. So to calculate its mechanical energy at that point is simply m times g times h. So we take our mass, 0.250 kilograms, times 9.81 times 0.25 meters, because it was 25 centimeters above the ground at that point. Everybody okay with that? All right. So if we punch all that in, okay, so we got 0.613 joules. Okay, is our mechanical energy at its highest point. Now, obviously I did not pick this question for its mathematical trickiness or anything like that. Well, sort of, actually. Okay. What's the mechanical energy of the pendulum relative to the floor when it's at its lowest point? 0.613 joules. If I put this question on a test, I will have people go through all of the work to prove that to me again. Okay, they'll go, okay, it's got this much potential energy, its EP is m times g times h, because it's still, let's say, 5 centimeters above the floor, and then they try and figure out how fast it's going. Okay, and this is actually kind of like a final exam question or a Unit 4 exam question, okay, where we talk about conservation of energy, but we also know more about a pendulum, so people are figuring out what the maximum speed of the pendulum is going to be, and then they're doing all this work, and then they get that number and they go, like, there's 10 minutes of my life I won't get back. Okay? If we understand the law of conservation of energy, this question takes us 10 seconds. Okay? 0.25 times 9.81 times 0.25, and we're done. That's the answer basically for, well, A and B. Okay? And even for C. Well, not really, because there's still some potential energy there at the bottom, but okay, it's not too difficult to calculate that. Okay, calculating the speed of the pendulum bob at its lowest point would just be manipulation, kind of like what we did yesterday. Okay, but all I wanted to do with that question really was to illustrate that, remember, if you calculate the mechanical energy anywhere, it's everywhere. Okay, that anywhere applies to everywhere in that system. Okay, it cannot change because of the law of conservation of energy. Okay. All right. I want you guys to try number 2. Okay, so we have this model rocket. We know the mass is 3 kilograms. It's fired so that when it is 220 meters above the ground, it is traveling vertically upward at 165 meters per second. And at that point, its fuel runs out, so that the rest of its flight is without power. So there's no work being done after that point. Okay, obviously work is done to get it to that point, but after that, there's no work done on the rocket. Okay, so assume that the effect of air resistance is negligible and that all potential energies are measured from the ground. All right, I want you guys to answer A, B, C, and D. Okay. All right, so for part A, how do we calculate mechanical energy? With what? Right, potential plus kinetic. All right, so if I want to calculate mechanical energy, I just go EP plus EK, and I have enough information to calculate that because they tell me how fast it's going and how high it is and its mass, which is all I need. All right, so I'm going to go m times g times h plus 1/2 mv squared, so that'll be 3 times 9.81 times 220 plus 1/2 times 3 times 165 squared. So 3 times 9.81 times 220 plus 0.5 times 3 times 165 squared. Okay. 4.73 times 10 to the 4 joules. Okay, so part A, pretty straightforward. Part B, when it reaches the highest point in its trajectory, which is straight up, which is important for this, okay, straight up, what will its gravitational potential energy be? So if I got a rocket and it's going straight up in the air, when it gets to its highest point in its trajectory, how fast is it going? Right, that's why it's at its highest point. It can't go any further. It's going to turn around and fall back. Okay, so all of its energy then is potential. So I can just recycle this number for that answer. All of its mechanical energy will be potential. So that's one of those ones that's, you know, if you really recognize what's going on with energy, you can save yourself a lot of work. And probably for that one, yeah, a lot of work, because you'd have to do a bunch of acceleration calculations in order to get what its height would be and all of that kind of stuff. So yeah, recognizing saves you work. All right, for part B, how far above the ground is the rocket at its highest point? Well, if I know that number is its potential energy at that point, I can calculate its height. Height will be the potential energy divided by m times g, so 4.73 times 10 to the 5 divided by 3 times 9.81. All right, so it's, well, exactly 1 mile above the Earth's surface. 1,607 meters. Okay, 1 mile above the Earth's surface. Okay, when it hits the ground, what is its speed? Okay, so when it hits the ground, all of its energy will be? Okay, can I use that number again? I can. Now it's going to be my kinetic energy, and I'm simply going to manipulate for V. And I'm going to say that VF will equal EK, which is my recycled number, divided by 1/2 of m, square rooted. Okay, so we take our 4.73, okay, and we divide that by times 1 point, or divided by 1.5. Don't know why I put that in brackets, or why I put a 9 after it. Okay, and then I square root that. All right, so it'll be going 178 meters per second when it hits the ground. Okay, everybody all right with that? All right, did that use the law of conservation of energy? It did, but not in a, well, I always do law of conservation of energy questions this way. I put EI equal EF, and I write them all out, and I expand it, and I manipulate. Sometimes I'm going to give you a question where it's a law of conservation of energy question, but it doesn't necessarily follow the pattern of all the problems we've done. It's more set up to check your understanding than to check your algebra. Okay? I already know you guys are good at algebra. I don't need to test that further, but I can use a question like this to test your understanding. Okay, let's do this pole vaulter question. Okay, so a pole vaulter with a mass of 56 kilograms tries to convert the kinetic energy of her approach into height. What is the maximum height she can expect to attain if her approach speed is 8 meters per second? Okay, and we want to assume that the center of mass of the vaulter is 0.850 meters above the ground. That rarely comes up, but it's also quite important. Okay, my mass is not distributed into a small box that's sitting on the ground. Okay, much of my mass is above the ground. Okay, and balance is important and related to where your center of mass is. It's why most sports involve you getting a little lower, so your center of mass, we call it the center of gravity, is lower. Okay, it makes you quicker, okay, because you can move that mass more quickly. Okay, if you're standing straight up and down, you're not very quick to move that way, as opposed to if your center of gravity is lower. Okay, that sort of makes sense. Okay, like especially like basketball when you're playing defense, right? Like you have to be really, really low. Football, same thing. You don't generally try to block from this position. Okay? In hockey, you don't generally try and hit from this position. Okay? You get low and you get your center of mass under something. Okay? So you can remain better balanced. So what they're saying here is that her mass is essentially 0.850 meters above the ground because her legs don't weigh very much. Okay? That sort of makes sense? It's just adding an extra little thing into that question. All right, give you guys a little bit of time to do that.